Hello, and welcome to the National Air and Space Museum. I am Dr. Jennifer Lavasser, a curator here in our Department of Space History, and I want to welcome all of you to What's New in Aerospace, our program this afternoon. Today, we are celebrating Earth Day, as well as the 25th anniversary of the Hubble Space Telescope. And we have Dr. Piers Sellers with us, who's going to talk about seeing Earth from space. He's going to give us a tour of Earth from the astronaut's perspective, and also show us what we can learn about our planet from orbit. I want to remind everyone who is watching online or on NASA television to please submit your questions, and we can answer them later in the show. Now, I want to introduce our speaker today. Dr. Sellers was born in Sussex, England, and before he went to university, he trained as a pilot with the Royal Air Force. He earned a Bachelor of Science degree in Ecological Science at the University of Edinburgh, and a PhD in Biometeorology from the University of Leeds. He moved to the United States in 1982 to work at the NASA Goddard Space Flight Center, which of course is just up the road from us, and he was there as a research meteorologist. I would say he is the model of persistence, having applied many times to the astronaut program, starting in 1984, and finally being accepted in 1996 as part of the largest class of astronauts ever, nicknamed the Sardines, because there were 44 astronauts in the class. He's flown to space 3 times on the space shuttle and spent almost 35 days in space. He twice flew on Atlantis in 2002 and 2010 to the International Space Station, and most importantly to us here at the museum, flew on Discovery in 2006 to the International Space Station. On his 2010 mission, he did a special task for us here at the museum. He flew a replica of a Nobel Prize won by John Mather from our collection to space and returned it to us quite generously at the end of his mission. He performed 6 spacewalks, totaling over 41 hours, having been spent outside his spacecraft. So let's welcome Dr. Piers Sellers.
Thank you, Jennifer. Thanks very much. Well, good afternoon, everybody. It's great to be here. And I'm going to give you a quick tour of the Earth from space. Anybody here like to go into space? I'm looking at the back there. Yes! Good answer. Yeah, the view is terrific. So I'm going to talk about planet Earth. I'm going to talk about planet Earth from over here, but there's less feedback. As if it were a human being and you were doing a health check on it, because really that's what our satellites allow us to do. So we're going to look at the vital signs of planet Earth. Here we go. Quick slide, there's me. These graphics are terrific. There you see the pulses going and all the rest of it. That's to get you in the mood for a medical examination of your home planet. And off we go. So here's what the planet looks like from space. I'm hanging from the space station, one-handed. See how strong I am? And from there, you're going around the world at 5 miles per second. Same as most of the other low Earth orbiting satellites. You're going around at 5 miles a second. You're going around the world once every 1.5 hours, more or less, 10 times a day. So you can imagine, you can cover a lot of territory and you can see a lot of stuff. All right, so let's see what we can see. The Earth system is really pretty complicated. This is based on data. This is not just made-up cartoon, but it sits in this little magnetic bubble. There's the magnetic field lines protected from particles streaming out from the sun. And there it is inside the magnetosphere. As you come down further and further into the system, you can start seeing the currents, and this is given to us by satellites, the currents of air moving around the planet. The fronts, the hurricanes, the depressions, all those kinds of things, the weather systems. As you come down even deeper, you can see how these air currents push the oceans along. That and various other things that make the ocean circulation go. And there you're looking at the Gulf Stream coming up the east coast of the United States. And now take a deep breath. Here we go, underwater. And all of this is based on data that we get from our satellite fleet in orbit. Oh no, that shouldn't have happened. Can you get us back on track? Terrific. All right. This is what you actually see with your eye, particularly at night. Now, what's the thing you notice? It's all the lights. Look at all the people, millions and millions of people, all doing stuff down there on Earth, all busy, all using energy and doing productive and creative things. So when you look at the world from space at night, it kind of looks like that. That's Italy. And you can see all the industrial regions, all the places where the big cities are, all the great cities lit up like Christmas trees. Just beautiful. United States, you can see the grid system of roads out in the middle of the country even, where all the towns are spaced out on a grid system. And look at the big East Coast conurbations. You are a little bright light somewhere on there. Okay. So, how do we know all this? How do we see all this? We have 18 satellites that belong to NASA that go around looking at all kinds of different things every day. They look at rainfall, snow, and we'll look at a few things that they can see. Some of them go around in orbits around the equator. Most of them go in orbits around the poles so they can cover the whole world every day. And some of them, you can see, we call the A train coming down the left-hand side of the screen. Some of them follow each other along so we can compare observations from them. And we actually correct each other using simultaneous observations. So here you are in space. This is a bit speeded up just to make you more exciting, okay? But here on space station, looking through the forward window, belting over the planet, and I'm going to show you some of the observations that we've been able to make only over the last 20 years since we've satellite system. First of all, insolation, that's the amount of sunlight hitting the world from outer space. And outgoing radiation is the stuff that's being lost to space. Precipitation, subsurface water, you can see. Leaf area, we can see the amount of green leaves on the planet, and also the amount of carbon dioxide in the atmosphere. These are observations we make from space all the time, every day, everywhere. The winds, oceans, the saltiness of the oceans. It's kind of a miracle to me that we can measure the saltiness of the surface ocean from space. Albedo means how bright the surface is, how reflective it is. Land temperature, its hotness. Various gases like carbon monoxide, nitrogen dioxide, those are pollutants. And last of all, gravity, disturbances in the gravity field and snow and ice. And I'll come back to that later. So we're looking at the world in all kinds of different ways and getting all these different kinds of data all the time. So I can't talk about all of it today, so I'm just going to talk about three things. I'm going to talk about the water cycle, as the oceans. I'm going to talk about the land biosphere, all the living things on the land that we can see from space. And last of all, I'm going to talk about what scientists call the cryosphere, but the people like you and me, it's ice and snow. Ice and snow everywhere around the world. Okay, so we're going to get cracking with the water cycle. So you take all the data from that satellites can see and you put it through a computer, and this is the flow of atmospheric water vapor around the world. You can see it kind of bubbles out of the equator, it gets transported around towards the poles and rains out. Here's the surface oceans. This is the temperature of the surface oceans as measured from space. So you can see how much warmer the equator is than the poles. That's kind of obvious, right? Where it's icy, it's cold, and in the middle of the world, it's warm. But look at the middle, coming off South America, going across the Pacific. You can see these kind of big waves moving across the Pacific. And that's due to planetary scale disturbances in the surface of the ocean. And that controls weather actually all over the Americas. El Niños and La Niñas, you've probably heard of those. So that's surface temperature, how warm the ocean is. This is salinity, or saltiness of the surface ocean, and we've only been able to do this since 2012. This is a brand new measurement. Before then, the only thing we knew about saltiness of the ocean was when people stuck a bucket in the water and measured the saltiness on a ship. So now we can see it all over the place. And if you look carefully, you can see some really interesting things. Look at the Amazon. Where the Amazon comes out of the Atlantic, you can see a kind of blue tongue of fresh water coming out. You can see that the Atlantic is a lot saltier than the Pacific, and that's because it rains harder in the Pacific. There's more fresh water on the surface. And you can see lots of fresh water up where the ice melts in the summer in the northern ice cap and down by Antarctica. So very interesting patterns in salinity that we could never observe before. Now, salt in water makes it heavy. Okay, it's a little bit heavier than fresh water. That's why you float so well in the Dead Sea, in the Mediterranean. And also, hot water is lighter than cold water. And knowing these two things, how hot the water is and how salty it is, allows you to make a predictive model of the ocean's circulation. So a computer here is simulating, based on those observations, where all the water is going and how it's flowing. And we've known this for years, but now we know it in great detail. There's a huge conveyor belt of water around the planet. This water goes round and round Antarctica and spins off these loops that go up into the great ocean basins. It goes out pretty quickly towards the North Pole and then sinks and comes back very slowly across the ocean bottoms. But quite an amazing thing. In the atmosphere, water vapor moves around as clouds or just like steam. It looks like steam, water vapor coming out of your kettle. And here the observations from space, again put into a computer, we can find out how much water is moving through the atmosphere and where it's going. A lot of it gets moved around by storms, as you would imagine. In fact, hurricanes move a lot of the water vapor away from the equator towards the higher latitudes, where they break up and then drop all their water over the continents. Okay, the latest thing in the satellite fleet that we just launched about a year ago was the Global Precipitation mission. So it's a big machine. It was built up at Goddard, which is just down the road from here. It's about the size of a school bus, and it has a radar that can see inside clouds and see the rain as it's falling, as well as a radiometer that maps the precipitation over wide areas. So this thing scoots around the world 10 times a day. Here it comes, meow. And it kind of vacuum cleans its way around the world, leaving a little stripe of data and taking these measurements and showing us what it's got. But it's not alone. There are 8 other satellites that belong to, some for the US, but mostly to other countries, Japan, France, Europe, Korea. And we all combine our data to get an idea of precipitation around the world all the time. Every 3 hours, in fact, a satellite's going over and measuring rainfall. So one really spectacular example of the observation that you can get from these new satellites, here's GPM shooting over the United States during the March snowstorm. And you can see the warm colors are rain, but the blue colors are snow. So the first time we can actually see snow falling in the clouds, then turning into rain, is it gets low in the atmosphere, then falling on the ground. Come around, it's those kind of flat blue puddles. That's snow that's actually accumulated on the ground. We're seeing the stuff falling, and we're seeing it accumulate on the ground. It's very powerful. So all of this stuff is useful. We need to know about precipitation. We need to know about the water cycle. Why is it important? Well, no one likes to be flooded. No one likes to be in a drought. And no one likes to have a landslide fall on top of them. So we can't stop those things from space, but we can tell you if they're going to happen, and we can keep an eye on them as they develop. So forewarning is vital. And I think any of you who've lived down in the Gulf states, like I have, down there in Texas, having a 3-day warning for a hurricane is really good. It allows you to get the dog and the cat in the boxes and out to somewhere safe. All right, next we're going to talk about the land biosphere. For about 30 years now, we've had satellites that can see greenness, green vegetation. And this is a speeded up movie showing not only the vegetation on land, but also the plankton in the world's oceans. So you can see as the seasons change, you've got this green wave that moves up and down the planet. So every summer, you have this wave of greenness that goes all the way up through North America, and then in the winter, it falls back down again. And here we are, we've spread it all out, we've calculated how much production, how much growth there is based on these measurements. So here you are, you're looking at how much wood or tissue or any bits of plant are being made every time a green leaf fixes sunlight and does photosynthesis. So you're actually looking at the heartbeat of the planet here. Every year, it sucks down carbon dioxide into green living things, and every winter, it throws it back out again. One of the ways that all this growth gets back into the atmosphere is, of course, through burning forests, volcanoes, but a lot of carbon dioxide that gets into the atmosphere comes from power production and us driving around in cars. Oops, I'm going to go back one. Sorry, I was a bit quick. I can't go forward on this. Never mind. Okay, so over time, because we've been burning fossil fuels and running around in cars and things, the amount of carbon dioxide has accumulated in the atmosphere. But it doesn't go up steadily. If you look, every year it goes up and down in a kind of cycle. And that's because every summer, all the green forests in the northern hemisphere suck down carbon dioxide, so it goes down a bit, and in the winter, it comes back out again. So you see this annual cycle. And of course, every year we're adding a little bit more carbon dioxide through fossil fuel burning, so the trend is overall upwards. Now the changing colors you can see there are observations of carbon dioxide from satellite. And you'll notice that more carbon dioxide is produced in the northern hemisphere than the southern hemisphere. And that's because most of us live there. Most of us live in the northern hemisphere. That's where the industry is. That's where all our cars are driving around. So that's where most of the carbon dioxide gets released. And that's what the satellite tells us. Okay, so we can put these two bits of information together. The kind of yellow smoky stuff is a satellite observation of carbon dioxide, and the green on the surface is vegetation. And you can see how there's sort of a correlation between the two. That when it starts to green up in the northern hemisphere, it sucks down the carbon dioxide into the trees, and in the winter, when it all dies, the carbon dioxide comes back out again. So two different satellites are telling us where the carbon dioxide's going. A lot of it gets sucked into the trees, and about the same amount actually gets into the ocean. Fires, as one way carbon dioxide gets back. That's how dead vegetation very quickly sends stuff back into the atmosphere. And this is a satellite picture showing you all the fires in Africa as observed from space, changing over the year. What's happening here actually is people, they grow their crops, and at the end of the season, you've got all this dry stubble, dry trash. They just burn it, right? So that it's fertilizing the fields for the next year. So this has been going on for thousands of years. This is how people make a living. But you can actually see it from space. So someone down there is working hard. Other things we can see from space. Here's Las Vegas. Anybody here from Las Vegas? Yay. Well, it's got bigger. Look at all those golf courses. Look at all those new houses and things. And as Las Vegas has got bigger over the years, this is Landsat data, you can see that for Lake Mead has got smaller. There's been some dry years, and that combined with increased demand has slurped down the lake a little bit. You probably know that. It's the lowest it's ever been right now, that's right. Big city, about twice as big as it was. So we've been looking at this for the last 30 years. Other things we can see from space, all kinds of stuff. Here's some mining activity in West Virginia where they cut off the top of the mountain to get at the coal. And as they move out, it slowly grows back. We've got a flat mountain after that. And all kinds of different things. Here's Saudi Arabia. And what you're seeing is people drilling for water and then starting irrigation and growing vegetables in the middle of the desert. So an incredible amount of effort to grow food for local markets out there in Saudi Arabia. And this is true across the whole Middle East. If you've got enough energy to get the water out from very deep levels, you can have yourself a lettuce. All right, so I've been talking about carbon dioxide in the atmosphere, and that helps to increase the temperature of the atmosphere. And since we've been watching since 1890 and making careful measurements of atmospheric temperature, the world has got warmer. And I want you to look at this picture very carefully and see if you could tell me two things about what's going on. So we're coming to the 90s, the world's getting warmer. And there we stopped at 2013. So what two things can you tell me? It's got warmer everywhere, but where does it get warmer most quickly? North Pole. It's twice as warm, 2.5 times warmer at the North Pole than at the planetary average. Now, why is that exactly? There's a very good reason. We'll get to it. I'm going to tell you, so I bet you know the answer, but I'll show you. Okay, it's warming up at the North Pole because the ice has been decreasing over the last century, as far as we can tell. We've only been watching it from space since 1979, but the amount of Arctic sea ice is decreasing. And what happens when you melt nice, white, bright ice that reflects sunlight? You expose pretty much black water, and that absorbs sunlight, warms up a bit more, and nibbles away at another bit of ice. So it's a runaway feedback. As the water gets warmer, it melts more ice, which warms more water, which melts more ice. So it accelerates. And you can see how over the last decade or so, there's been a real downturn in Arctic sea ice. And our models predict if this keeps going, you'll be able to get in a kayak sometime maybe in the 2060s or 2070s and kayak right over the North Pole in the middle of summer. There won't be any ice. You'll be able to go right over the top. It'll freeze up again in the winter when it gets real cold, but you'll have an ice-free polar ocean at the end of summer. So these are all satellite observations. We have a satellite that can see through clouds and can measure the amount of ice area very well. It's been doing that for about 30 years. And this is the observation turned into a kind of a movie. And you can see ice isn't this sort of static, boring stuff. It moves around depending on the winds and the currents. It's kind of alive. Here it is. Here's winter ice up. And the ice slides down around Greenland and Iceland, and kind of like custard, moves around all over the place, and then retreats in the summer. But the winds and the currents make it move all over the place. And here's the winds, and you can see how the wind field tends to push the ice over on top of Greenland and Canada preferentially, and away from Alaska and the North Russian coast, which is why the ice extent is disappearing there faster. Okay, now there's another interesting thing is that the sea ice around Antarctica is about the same. It's not really changing much, or maybe even growing a tiny little bit, whereas in Arctic, it's decreasing a lot. Why is that? Well, Antarctica is a continent surrounded by an ocean, whereas the North Pole is an ocean surrounded by continents. Completely different systems. In Antarctica, there's a kind of a wind field that goes around there, and it helps keep the cold in. But even now, we're seeing decreasing ice on top of the continent, on top of Antarctica. One of the ways we do that, to find out where the ice is going, is to use a radar from space that can see how fast the ice is moving. And this is speeded up, okay, obviously. But you can see how the ice collects into glaciers and then drops into the oceans. First of all, I thought this was lemmings, but no, it's not. This is actually ice moving as seen by radar from space. Now, what's happening in Antarctica and Greenland is a process that's very simple, but people hadn't thought of it before. When the ice starts melting, some of the water wiggles its way down through the cracks in the ice, and it gets between the rock and the ice, and that acts like, like butter. And the ice can slide off more easily into the ocean. And on Greenland, we've seen the speed of the glaciers double quite recently over the last 20 years. So the accelerate, they call it the galloping glaciers. These guys are speeding up and falling into the ocean much quicker than they used to. And there's a magical way we can see this at work. We have two satellites that chase each other around the world. And when the lead one goes over something heavy, it drops down a little bit, and the trailing one measures its distance using radio and can see how fast it's gone down, and the reverse when the trailing one goes over something heavy. So you can keep track of the different amounts of material that's on the Earth's surface using this system. It's called GRACE. And basically, you can weigh the amount of ice on Greenland using this technique. You can figure out how much the mass of ice is stacked up on Greenland. And here you are since 2003, 2010, that's the only record we have since we invented this thing. And you can see that the ice goes down every summer as it melts, it recovers a bit in winter as it snows, it goes down again in the next summer, But overall, we're losing ice very fast at the rate of about 200 or 300 gigatons a year. Now, a gigaton is a cube of ice that's half a mile on a side. So that's a big cube of ice, okay? It's actually a kilometer on a side. So 200 to 300 gigatons of ice every year falling off Greenland into the ocean and not being replaced. That's significant. That's a lot. And we've had a satellite that's was observing the height of the ice early on in this decade. It only lasted about 3 years. So after that, we had a fill-in using aircraft. And here's aircraft bravely struggling through the polar ice clouds to measure the ice over Antarctica. It's a lot of fun, by the way. You know, stand up there in the window and look out, the ice just go blazing by. Quite beautiful. But there's a whole lot of instruments here that are measuring the amount of snow and ice that's stacked up. This is Antarctica. All the mountains down there, really beautiful. And you're nice and warm in the ocean. You don't have to tough it out there like Amundsen or Scott or anything. So we're using aircraft now because we don't have a satellite to measure the ice depth. But very soon, in 2017, we hope we'll be launching a satellite that's going to use lasers to determine the exact height of the ice pack. And this will tell us how quickly the ice is going down. It'll also tell us how much ice there is in the oceans, and it'll tell us how quickly the ice is moving off the continents into the oceans. So that's something to look forward to. We've been working on that in Goddard for quite a while. Not too much, but we have many different ways of estimating the amount of ice, and they sort of agree. They're completely independent methods, they sort of agree, and they're showing that on average we're losing about 250 gigatons of ice off the landmass into the oceans every year. So where does it go? Well, a couple of things are going on. The ocean's getting warmer, a bit warmer every year, so it's getting thicker and fatter because water swells up a little bit as it gets warmer. That's the amount of in the oceans. And if you combine the ice that's falling in off the Greenland and Antarctica with the warming of the oceans, the sea height goes up. And here we see we're measuring sea level from space using lasers from 93 to 2015, and that's about 3 inches. It's gone up about 3 inches over that time. We've actually seen the sea level all around the world go up about 3 inches. So what's going to happen? Well, we think, because the ice loss will accelerate, that most likely between now and the end of this century, 2100, sea level will rise probably 1, 2, 3 feet, something like that, about that much, quite a lot, which is not a problem in DC, but in Florida and Bangladesh and a lot of coastal regions, you know, is something to think about. So all my friends who work on the ice, they like to go out there and you see them working away on the ice. And if you look, there's 2 interested spectators. The penguins always like to come and watch people working away. You see there's 2 penguins standing there at the edge, the top left. And they can sit there taking notes and see what they can find out. They're curious creatures. You saw a penguin? Good for you. So this is a computer model of Earth. So all the satellite observations we get, we put in a computer model, combine them, and do a gazillion calculations, and can calculate the movement of air currents and clouds. And you can see this looks like the real thing. This is a computer simulation, and we use it for prediction. Weather prediction, and another version for climate prediction. But look how realistic it is. You can see all the little cumulus clouds, the little puffy clouds. You can see giant streams of air going across the oceans. You can see ice coming and going and snow coming and going over the land. And you can see the greenness changing. This is all a simulation, but a realistic one. It's a little toy world. And that's what we use to try and understand the Earth system. That's how we try and make sense of it all. So is this useful? Yeah, you bet. Here comes Sandy. There comes Sandy. Look at it. Well, 3 days ahead, before it turned left and whacked into New York and New Jersey, we knew it was going to do that with high confidence. We knew it was going to head out in the Atlantic and then turn left and come back in. Why was that useful? Well, everybody in New Jersey and New York was happy because they got to know 3 days ahead of time that it was going to hit them. But think of all the people on the eastern seaboard who didn't live in New Jersey or New York, who did not have to evacuate, who didn't have to pick up everything and go. So there's a massive avoided cost from knowing what the weather's going to do to you. This wasn't possible 20 years ago. It wasn't even possible 10 years ago. So there's one advantage of the whole satellite modeling system. Tells you a lot. So this is what the world's going to look like in 20 years. I'm just kidding, it's the sun. That's all right. There's a sun. All right. This is a picture of the sun taken from another satellite. And these things are called coronal mass ejections. Are really cool. This is where the sun throws out a whole lot of gas and stuff, and it gets twisted around in magnetic fields and falls back down again. Very dramatic, but you don't want to get too close. You'll lose your eyebrows. Some people thought for a while that changes in the solar output, how productive, how hot the sun was, made changes in weather. Well, that's true over the millions and millions of years time scale, or the billions of year time scale, but it's not the cause of the recent warming. It's the carbon dioxide that we're putting in the atmosphere. But it's a cool picture. So I just had to show it. Talk about that. So all the wisdom, all the models and things that we use to one graph. This is the sort of billion-dollar graph, if you like. And what it is the amount of warming that we can expect to get in the century is completely related to how much oil and gas we burn. So I want you to look at where it says 500 gigatons of carbon burned on the bottom. That's where we are now. We've increased the temperature of the Earth by 1 degree grade. That's 1 Fahrenheit. From the beginning of the evolution, we dug up a bit of coal and decided to burn it. Not a bad thing. That's why we all have these beautiful, buildings, good life. Without the Industrial Revolution, I wouldn't be standing here with a clicker. All right, so here for that. But you can see if we kept doing what we're doing, it's unlikely. The coal there was, we'd have a very hot planet, 4 degrees warmer, and that wouldn't be very healthy in a lot of places. So somewhere between now and 2100, we're probably going to change the way we do things. And by every indication, we'll be able to level off somewhere between 2 and 3 degree warming. Quite likely. Why am I optimistic that people make the right choice? Because we have an example. Who here remembers the ozone hole? There you go. So there was a hole in the ozone over Antarctica. We could see it with a satellite. Oh no, it's growing through the 80s and 90s and the early 2000s. So what happened? Well, the scientists said it's happening. They reported the satellite data. They went down to Antarctica and measured all the ozone. They did all that stuff. And then they came and told the UN, and the UN got all the countries in the world, and they signed all these treaties that reduced the amount of material that was going up there that was eating up the ozone hole. It took years. I mean, look at all these treaties. It took forever to do it. You've probably heard the Montreal Protocol was the first one. By the way, there's one of our scientists sitting at the back eating some chips. His name is Paul Newman. He's not related to the other Paul Newman, but he was one of the guys who found the ozone hole and did the work to persuade politicians that probably ought to do something about it. So as a result of policymakers working really hard to understand the problem and passing the right laws, we have the world that's projected if we hadn't done anything, and the world the world projected, which is what we think is going to happen now. We've got these laws in place, and the world avoided, which what would have happened if we'd kept eating away at the ozone hole. Around about 2040, you can see there's ozone is almost disappearing in the right-hand screen, which is what would have happened. At this point, you've got crop damage, a lot of health risks to people. The plankton on the surface ocean is in pretty bad shape. So we avoided that. We woke up, we did things, we avoided that, and we expect to have actually a world that's pre-ozone hole by the 2060s. We'll be back to where we should be. So we will have fixed the problem. Not bad. So, reasons for optimism. This is the world in Christmas 1968, and there's 3 billion people out there on that planet, minus 3, because 3 of them had to be in a spacecraft taking this photo, okay? So 3 billion people in 1968. And here is 7 billion people now in all the cities of the world, more than half them in the cities of the world now. There's 7 billion people, minus 6 who are on space station. Okay, there you go. So there's a lot of us there. So, you know, so far we've managed to do a pretty good job of getting from 3 billion to 7 billion without, you know, totally destroying the planet. We're doing quite well. So that's why I'm optimistic. Because I believe that everybody who's born, all you young people out there, you're smart, you're resourceful, and you bring the solutions with you that'll help get us where we should be going and fix the problems that confront us. I have great faith in the resourcefulness of human beings. So with that, I'll stop right there. Thanks very much.
All right, come have a seat and we'll do some questions.
All right. That was me, by the way. No, it wasn't. I wasn't nearly that good looking.
Well, I wanted to ask a question first. As an astronaut and someone who's traveled to the International Space Station, you're traveling about 220 miles above the Earth.
Right.
How far up are the satellites that are making these observations?
Very few of them are down there because there's quite a lot of drag from the atmosphere. Most of them, the ones that I was showing, they're up there at about 700 kilometers, which is about 500 miles. 500 miles up. But they still go around the world about 1 hour. Takes them an hour and 40 minutes to get around.
And when you were up in space those different times, did you make any observations of your own, either with a photograph or just your eyes, of changes that you were seeing over the course of those years?
One thing, I didn't see changes between the missions that I could tell, but you could see where people were. You could see the cities in the west, like Europe and North America, very clean. So for the last 20 years, apparently, all the Clean Air Acts have cleaned up the air over the cities. The air is good. A lot of the industrial centers in India and China, very thick smog. You can see there still, because they're still burning a lot of coal to do their industry.
Let's go to a question from the audience.
When you go into space, how do you, when you're very close to the Earth, how do you not fall down?
How do you not fall down on the Earth? Okay,
No, like when you're very close to it, when you
Okay.
take that video.
It's one of these amazing things that what happens is if you go really, really fast around the world, if you go really fast, you are falling, but the world is curving away from you at the same rate that you're falling. So you're always falling. You just keep falling around the world. You never actually hit it. But you have to be going very fast to do that. You have to be going 5 miles per second. All right? Whew. That's fast. Good question, though.
Next question for
We have an online question next.
all right. We have an online question.
What technological advancements in your career has had the greatest impact on our ability to study the Earth?
I would say it's a combination of things. To my mind, it's been a combination of satellite sensors that we wouldn't even dreamed of, 30 years ago. 30 years ago, we're using stuff that's not much better than a TV camera to look at the world. Now we're looking at it in all different ways. We're using radars and all kinds of instruments. And that's good. I mean, we're seeing things we've never seen before. But to my mind, the thing that's made the biggest difference really is computing power. We've got computers now that my iPhone now could do more than sort of computers when I was a college student that would take up a room. So computing power has allowed us to simulate the world at a very fine resolution, very realistically, not possible 20 years ago. It's a huge help. It's really tough to do it all by hand, let me tell you.
We have another question from the audience.
How did y'all get the camera that y'all had to show us?
How did they get the what?
The camera from the moon.
How did you get the camera from the moon?
Oh, earlier we had an Apollo 11 Hasselblad camera here, and she wants to know how we got that from the moon. The astronauts actually brought that back with them. It was with them in the spacecraft when they came back, and you can actually go just a few doors down here over in our Milestones of Flight gallery and see the spacecraft it came back in. So it was protected as it came back through the atmosphere.
Yeah, and it's government property, so those guys, they have to bring it back. Or if not, this comes out of their pay. Yeah, I know about that.
How many days did it take y'all to come back to Earth?
How many days does it take to come back?
Okay, you know what? This is amazing. When you're going around the world on the space station or in the space shuttle, and the engines kick in to bring you back to Earth on the space shuttle, about an hour later, you're back on the ground. It takes an hour. Now, if you're at the moon and you decide to come back, it takes about 2.5 days. 2.5 days. You're falling all the way home. It takes about 2.5 days.
Another question from the audience?
If it's daytime and you go up to the moon, will it still be dark?
Oh, so if it's daytime here, it's going to be dark on the moon.
No. If you look up, sometimes during the day, you can see the moon on a very clear day. Have you ever seen that? Have you ever seen that? Yeah, the moon goes around the world very slowly, so for like half the time it's bright and you can see it, and the other half time it's darker. But you can see it during the day too.
An online question?
We do have an online question next. How has atmospheric pollution changed over time? Is it something to be concerned about?
Okay, well that's a complicated question, but first of all, let's talk about the atmospheric pollution that's around the cities, around industry. That has got a lot better in the developed world over the last 20 years. And we can see that from space. We can see how all the cities in Europe and in North America have cleaned up enormously. So you can all be thankful for, all the legislation that did that. In other parts of the world, as I said earlier, pollution around cities has actually got worse because people are developing very fast. The thing that, is most worry to Earth scientists like me is the increase in carbon dioxide over time, which gives you a climate change. But that increase in carbon dioxide isn't dangerous to you and me health-wise. If I breathe in a little bit more carbon dioxide, it doesn't hurt me. It's what it does to the climate system.
Another question from the audience.
How heavy is the spacesuit even when you're in it when there's no gravity on the moon?
Boy, yeah.
How heavy is the spacesuit when you're wearing
Oh,
it?
the spacesuit, it's heavy. It's about 2 times as much as I weigh, just the spacesuit. But when you're in space, you're weightless, so you don't even feel it. You don't even feel it. But if I wore it on the ground, I'd fall over.
Another audience question?
What will happen if we still burn coal till the 21st century, to the 2000, till the next century?
If we still keep burning coal, at the rate that we're doing now, all the way up through 2100, and I think this is unlikely for the reasons I said, but if we did, we'd have a very warm world and the climate patterns would be very different. And in fact, when you get that warm, it's not really clear what kind of a world we would have. I think there'd be quite a lot of problems. So I'm pretty sure between now and then, people like you will help figure out a way to do things better.
Another audience question?
What do it feel like when you're in a spacesuit?
What does it feel like when you're in a spacesuit? It feels very comfortable because the spacesuit is floating and you're floating inside the spacesuit. So you're just kind of bumping off the inside. It's very, very comfortable. And the thing that's not so comfortable is when you try and move your hands or your arms because the spacesuit fights back. So you have to kind of crunch your fingers like that to make a grip.
We have another online question. What has been the most surprising thing you have learned about the Earth in all your research?
Well, let's think about that. I was really surprised at how big an influence all the living things on the world have on the climate system. That was that basically the biology of the Earth has a big impact on the climate and the way things work. And in fact, that the whole biosphere is reacting to the increase in CO2 by sucking down more carbon dioxide. It's actually helping us out. So, you have to pay attention to global biology, which is something we hadn't even thought of 30 years ago. It's a brand new science.
Actually, I want to jump in there. We hear a lot about deforestation, especially in the Amazon. Are we noticing a lot of changes in that particular region because of the loss of those plants?
No. What's happened is there was massive loss, deforestation with development about 15, 20 years ago. But with changes in policies, that slowed quite a lot. And the other thing is we've seen, actually in North America, a large regrowth of forests, particularly on the eastern seaboard. All the way up and down around here, forests have been regrowing. Yeah.
That's great. Another audience question?
What do it look like in space? What do the Earth look like in space?
Oh, what does it look like? What do we look like here?
Yeah, we look, yeah. The Earth, let me tell you what you can see from up there. You can look down and you can look down at a city and you can recognize the outline of the city from your geography. You can see rivers, you can see ship wakes, ships going across the ocean. You can even see airliner contrails going across the Atlantic. You can see planes very slowly below you while you're spacewalking, pushing their way across the Atlantic. You can't see the plane, but you see the little white tail coming out from behind it. So you can see things that people make, cities, planes, ships, almost, and still go around the world in an hour and a half. So the world is a small place. The world is a very small place.
Another audience question?
Hi.
How do you get the things that fly around over the Earth to take pictures?
How do we get the things up into space that look down to take the pictures?
Great question. That's the difficult bit. We use one of those, a rocket. So we use a big rocket, and the bit that ends up in space is only about the size of a refrigerator. So you have a huge, great rocket and the thing up there on the top, the side of the refrigerator. But here's the difficult bit. That thing is so delicate, so precious, so expensive and hard to make. I'm amazed it survives the ride up into space. And then it gets hot and it gets cold, it gets shaken to bits on the way up, and it still works. So people have got really good at making this stuff.
Online question. Did your work as a shuttle astronaut relate directly to your climate research?
Honest answer, not really. So I was a climate scientist before I became an astronaut, and I think it's useful to have people who know all parts of Earth science in the astronaut office, and that was me. But most of the time I was worrying about how to build a space station along with all my friends.
Another audience question.
How do you sleep in space without floating away?
Oh, that is a great question. Let me, Jennifer, could you hold this?
Of course.
Let me show you what happens to my friends when they try to go to sleep in space. The first day or so. They look like this. They get in their sleeping bag, just tied to the wall, and they go like this. And that's because when you close your eyes and you start to go to sleep, you feel like you're falling. You feel like you just fell off a 10-story building because your eyes aren't telling you that everything's the same. And so some part of your brain says, wake up. So to kind of fool yourself, you tie yourself to the wall using bungee straps like this, and pretend you're at home in bed. But I always found it hard to sleep in space. But let me tell you a story. People who are up there for a long time, like for 1, 2, 3 months, they get used to it. And I have a Russian friend, and he'd just look at me and say, "Oh, Piers, I want to sleep now." And he would go to sleep in the middle of the room, and he'd just float around. But he was used to it. Good question. It's hard to sleep in space. It's very hard.
My question is, how many planets there are up in space?
How many planets?
How many planets are there up in space? Well, there used to be 9 around our sun, but one of them got demoted, and it's not really a planet anymore.
Got kicked out of the club.
Got kicked out of the club, Pluto. But let me tell you something else. We've been looking around other stars out there, and we think we have found 3,000 other planets just around the stars that are closest to us. Every solar system we look at has planets. So we think the galaxy is lousy with planets. They're all over the place, all different kinds, shapes, sizes. Lots like Jupiter, big, fat, gassy ones, quite a few rocky planets. They're all over the place. We found 3,000 so far, just in 10 years of looking. So that's going to be the exciting thing for you kids back there, is looking further and further out and looking at planets more and more precisely. Who knows what we'll see? Can we make another planet? Probably we could make another planet. I think it'd be hard. I think it'd be hard. We'd have to glue bits of asteroid together maybe. I don't know.
We do have an online question. What was the biggest setback in your research or your career? How did you overcome it?
Oh, well, that's a good question. I think the biggest setback collectively for all of us who are working on trying to build a space station in the astronaut office was the loss of the Space Shuttle Columbia. It was a terrible thing. You know, we lost some friends, and the program just came to a grinding halt for like 2.5 years. That was really tough on everybody. Tough on NASA, tough on the United States, and tough on the people who we lost and their families. And we just worked hard and got over it. Came back.
Another audience question?
What was your favorite time to go to space? The first time you went there, or the second time you went there, or the third time?
Oh, that's a great question. You know what? My second mission was my favorite. We launched on the 4th of July.
Ooh.
The only shuttle mission ever to launch on the 4th of July. So we had burgers for breakfast, get us in the mood. And it was just a great mission, lots of spacewalks, a lot of exciting things happening. It was a lot of fun.
Now, I mentioned earlier that you took a replica Nobel Prize up on that mission. Tell the audience what else you took on that mission.
Oh, yes. So I called the Royal Society of London and said, is there anything you'd like me to take up into space? And they said, yeah, how about a piece of Isaac Newton's apple tree? So when Isaac Newton died, they sawed up his apple tree and kept it in the museum. So I took a piece up with me, and then I held it up there in space, and I took my hand away to see if it would fall like the apple. And no, it didn't. But I know, and I did this for a school's lecture, and I said, kids, do you think Sir Isaac would have been fooled by this? And I said, no. Isaac would have known that actually the bit of apple tree is falling, but so is the whole space station around it falling at the same rate, so it doesn't appear to move. So Sir Isaac would have known better.
We have another online question.
I had to give it back, by the way. Yeah.
Do you ever dream about weightlessness?
Yes, I do. I do. I dream about weightlessness, and I dream about going in from blinding light to dark, because when you're whipping around the world in space, that's what happens. It's blinding, most beautiful sunlight you've ever seen. All the colors, as bright as anything, bam, a few seconds later, pitch black, you're nighttime on the backside of the world, and you're seeing thunderstorm flashes below you. That's a compensation in the cities. But you're seeing other things at night going on below you, but white, black, it's that's the way it is when you're whipping around the world.
Well, thank you so much for joining us today. We want to thank Boeing, our sponsors of the What's New in Aerospace series, Dr. Sellers for joining us and giving us a really interesting tour of Earth from outer space, and also to NASA for their partnership on this program. Thank you all for joining us.
Thank you. Thank you, Karen.
It was great.